So now we're going to talk about applied hash functions, and particularly we'll focus on the property of fingerprinting. So we can use hash functions for fingerprinting. And first we'll recap shortly what a hash function is, and particularly the properties that it provides. And then we'll start talking about fingerprinting and particularly two examples, BitTorrent and Git, and how they rely on the fingerprinting properties of a hash function. So let's get started with what a hash function is. So a hash function usually has three desirable properties that we like. Pre-image resistance, which is sometimes called one-wayness, and second pre-image resistance, which is sometimes called weak collision resistance, and finally collision resistance, or sometimes known as strong collision resistance, depending on which part of the literature you're reading. Various authors use different names for these properties. So the first one, pre-image resistance, simply says that we have a hash function, edge, with and we also get a value y. And the thing we're going to do, we're going to solve, is that we're going to find any x such that edge of x is y. So we get a hash function, we get an output from a hash function, and the problem we need to solve to break pre-image resistance is to find an x such that this equation holds. So that's pre-image resistance. So if this is very hard to do, then we say that the function edge here is pre-image resistant. The second property, second pre-image resistance, is related. But here the problem is slightly different, the problem that we need to solve to break pre-image resistance. So we get a hash function edge as input, and we get a value edge, x, as input. So here we get an input value, not an output value as with pre-image resistance. Now, what we are supposed to output is any value x prime such that edge of x is equal to edge of x prime. And of course, x prime should not be equal to x, of course, because otherwise the challenge is trivial. And if this problem is very difficult to solve, then we say that the function edge is second pre-image resistant. The third property is collision resistance. Of course, it's also related, intricately related to the previous two. But in this case, we just get the function edge. And now we have total freedom. We can find any two x and x prime, and they must, of course, not be the same. So two distinct x's, x and x prime, such that edge of x is equal to edge of x prime. And if this problem is very hard, then we say that the function edge is collision resistant, or strongly collision resistant, depending on the terminology used. So these are the three properties that we want from a hash function. So let's get started with fingerprinting. So another property that we want is compression. So we want a function f to be compressing, which means that if we have a function from some input set, so bit strings of length L, and the output is bit strings of length L prime, then we want to be able to have that L is larger than L prime. So we can have large input mapping to smaller output. And the reason for this is that, of course, we want a fingerprint to be smaller than the thing we want to fingerprint, because otherwise we might just as well use the data itself that we want to compute a fingerprint for. And that's unnecessary. We want to have something smaller. Fortunately, most hash functions provide this property that they are compressing. So, for example, if we use SHA-256, for instance, and we have some large input. So, for instance, this is the VirtualBox disk image for some Windows development evaluation, and that one is 43 gigabytes in size. Then we would like to have something shorter as a fingerprint. So take these 43 gigabytes, and then we have a most probably unique fingerprint for it. And we can compute that with the SHA-256 hash function. So if we do this, we see that it takes quite some time to go through all these 43 gigabytes of data and compute the hash, but out comes the hash value here for this VirtualBox disk image. And yeah, this since this is a hash function, a cryptographic hash function, it has the properties we talked about before. So it's highly unlikely that we would find something else that would result in the same string. So we can be fairly confident that we can use this string as a fingerprint. So a sort of short unique identifier for this particular disk image. And if anything changes in this disk image, then this fingerprint will also change, so we know that it's modified. So the requirements that we have is this compressing property that we've seen. So we could compress 43 gigabytes into a short string. So this is to make the fingerprint small. We also want the collision resistance property, because this reduces likelihood of collisions. And if we want to use these strings for some type of authentication, then of course we want the cryptographic collision resistance, not any weaker type of collision resistance. So let's get into our examples. So BitTorrent. So the idea of BitTorrent is that when we download something, we have Bob here who wants to share this file with 5 other people. So he sends a copy to Alice, he sends a copy to Carol, he sends a copy to David, he sends a copy to Eric, and he sends a copy to Hubert. In the idea of BitTorrent or peer-to-peer systems in general, so BitTorrent is an example of a peer-to-peer system, then we will use the fact that as soon as Bob has sent some part to one of the clients, that client can start sharing those pieces with other peers that are also downloading this one. This means that we decrease the pressure on Bob. So for instance, in this case, I mean, he had to upload 5 different copies, it took a lot of his bandwidth. Whereas in this case, he might only have to upload 3 copies, and the others share the load of distributing this piece of data among each other. So that's the general idea. So the question is, how do we get the most out of this peer-to-peer case? Well, the thing is we must keep track of different parts of a file so that they can share different parts. So the idea is that we take the file and divide it into small different parts. And then Bob can keep track of which parts he has sent to different people and send those parts that they want. And these people know which parts they have in full, so they can share those parts with other people. And people can coordinate around these much smaller parts of a file. So instead of say that Bob wants to distribute this disk image, which was 43 gigabytes, then he might divide it into a few megabytes each, these parts, and then transmit part by part to different people, and then they can start distributing these parts to each other. Because then they have much smaller blocks to work with, and they just keep track of which parts they have and which parts they don't have. And then the question is, they want to check that they actually got the parts that they were supposed to and they got them correctly. And this is where the hash function and fingerprinting comes in. So what we do is that Bob, he computes the hash of the whole file, and he also computes the hashes for the small parts. And these hashes will work as identifiers for these parts. And then they can use these to identify the parts that they need. And they can also use them to verify the integrity of the file and the individual parts once they receive them. So once they receive the data, they can compute the hash of the data and see, is this indeed the hash value that I expect. And once they have all the parts, they can compute the hash value of the whole file and see that they've received all the parts correctly, so they have the file and it's correct. So they can use the hash function for this. Now, why would we want a cryptographic hash function for this scenario? So we need the cryptographic hash function, so we need the strict collision resistance property of a hash function if we want any authenticity properties. For instance, will a malicious actor try to inject fake parts of files? Because in that case, normal, more error correcting or error detecting hash functions, they might not be strong enough to withstand a malicious attacker trying to modify a part so that the hash value will remain invariant, but the data itself is modified. But a cryptographic hash function will provide this property, so then you can be sure that it's very unlikely that a malicious actor has succeeded in this. However, to start with, I mean, for this to make sense, the hashes that you get must come through an authenticated channel. So normally these hashes are stored in what is called a torrent file. And that torrent file must, of course, be authenticated in one way. So get it through an authenticated channel from a person you trust, or it carry a digital signature or something like that. But if you don't have that, then the cryptographic hash function, the properties there is entirely pointless, since you don't know if the hashes are correct anyway. Then it doesn't really matter. So let's go to the next example, which is Git. Now, Git is a version control system for most people. But if you actually look into the details of how Git works, Git is actually a content addressable file system. So this is how it is if you look at its inner workings. Now, the reason it's content addressable is because everything in Git is a blob, or a binary large object. And the name of this blob is the hash value of the content plus a small internal header. And the content of this blob is just the content and nothing more. So no required structure on the inside or anything. It's just the content. And the name is the hash, as we said. So then the name depends on the content. And that's why it's content addressable, because it's the content that yields the particular name. So if you are looking for particular content, then you just compute its name and you can look for that. So for instance, we have these blobs here. There are 4 blobs. So we have the first one, which contains my foo and my bar content. And this, if we hash this, it might get the nice hash dead beef. And another blob which has the some kind of hello world program. Looks like it's Python by the syntax, and it might hash to dead code. So, and then we have some other blobs which hash to something else like ubablock and office. And these are just, yeah, you take the content, hash it in a particular way, and then you get the hash which serves as the name. It's as simple as that. Now, Git uses these blobs to do version management. Now, so for instance, if you want to implement a version management system or version control system, you need to keep track of the names of files. And the blobs don't do that, as we just said. They just keep track of content. And the names of those blobs are the hashes of that content. So we have another type of object in Git, which is called a tree object. And this allows us to keep track of some type of file structure. So, or rather a file tree. So the tree object is simply a blob, but where the content is structured in some predictable way. So it keeps track of like file mode, the type, whether it's a blob or if it's another tree, so a subtree, and a human readable name that we want to keep track of. So for instance, if we go back to our blobs, we see that these 2 blobs are in fact tree objects. So it contains the file system modes. So this says that this is a normal file with read permissions. It's a blob, so it just has some content. The name of the blob is dead beef, and then the human readable name is my file. So then we know that this refers to dead beef, so that's the content, and humans call it my file. And the other one is a directory. So we see that this blob is in fact a subdirectory in this world, or whatever to call it. And inside there is a file called hello pi by humans, and Git refers to it as dead code because that's the hash, and we see that this is the object that it refers to. So a tree, on the other hand, it doesn't keep track of versions, which is what most people think about when they talk about Git. So to keep track of versions, Git has one more type of object, which is called a commit. And this is yet another blob with structured content. And it keeps track of a tree object, which is the current state, and well, the current state of the files that we want to keep track of. It also keeps track of parent commits, which is what gives us the order of versions in Git. It also keeps track of the author and a commit log. So let's have another look. And now we've also added a commit. So we see we have this commit object down here. So it has a tree, which is ubablock, and the author was me, and the committer was also me, so it's the same person, and the commit log comment is initial commit here. So we see it refers to tree ubablock, which is this one. So this is the root of the state in this commit. And yeah, this one referred to dead beef. So this one, which is my file, and it also had a directory, which was this one, which contained hello.py because it referred to dead code here, which is this one. So we can see how these nicely link together to form a commit. And then a commit can, as we said, link to another commit. And depending on the order, you could get a different history, so to speak, and different outcome. So take a look at these Git objects and ask yourself, so what happened here? So this in this set of objects, we have two commit objects, one depending on the other. So in this case, we have the initial commit is ubablock, so this one, and what you should ask yourself is, what changes happened here? Think about that for a moment. Now, what actually happens here is that, yeah, we have this ubablock, which is the initial commit. So this one refers to the 8 bad food tree, which is this one, 8 bad food. This one has a blob, dead code, which is this one, dead code. And that's it. Then we have another commit, which is cool off, which points to the tree bios food, which is this one, which also has a human readable file name hello.py, so same file, but this time it refers to some other content. So this forbid hash, which is this one. So it seems like, and the parent, it says here also that the parent is ubablock. So it seems here that we went from this commit to this one, which means that we went from this code and rewrote it to this code. So we refactored our hello world program to use one print statement instead of two. So that's what happened here. Now, what properties do we actually want from the hash function in this case? Take a moment to think about that. Now, what we actually want is the compression property, because we want short identifiers. That's the entire purpose in this case. We also want collision resistance, and we want cryptographic collision resistance in case we want some type of authentication. We know that in Git you can actually sign your commits using a GPG key, so you actually get strong authentication in that case. So people sign commits. So that's in that case we really want it. Otherwise, if we don't care that much about the authentication property, then it's just to avoid two different objects colliding, because you don't want two different contents to get the same name, so to speak. And with a cryptographic hash function, we know that this is very unlikely to happen. And that was everything that I wanted to talk about. Thanks for listening.